All right, so in Chapter 4, Section 3, we are finally going to answer the question that I asked at the beginning that we've been dancing around. Well, how can we find the best line to model some data? Well, the idea behind this is in real life, if you go out into the field and gather data, whether it's economic data, scientific data, anything like that, the data will never exactly fall on a straight line. In fact, if it does, that is a significant statistical indicator that somebody is forging the data. Data in real life always has error in it, and it will always have other things, so it will never fall perfectly on any given mathematical curve. The best we can do is come up with something that approximates that. So to help us decide what kind of model we want to use for our data, it's often helpful to plot our observed data on a Cartesian coordinate system and then look at the data to help us determine what type of function might be the best to model it. So if I take a look here at example number 1, I've got this data set, and when I look at it, it's definitely not a perfect line, but if I were to look at my data, it seems to be fairly close to a line as I move from left to right. And we'll talk about what that means in a second. So the line that I drew here, does it have positive slope, negative slope, or zero slope? We've got negative slope, right? So we'll observe the slope of this line is negative. So we say the data is negatively correlated. So we're going to be talking a lot about the idea of a correlation coefficient. So when we have a set of data that we are modeling by a linear function, if the slope of our line is negative, the correlation coefficient will be negative. So if m is less than 0, the correlation coefficient if our slope were positive, then the correlation coefficient will be positive. So for us right now, we are only going to talk about correlation coefficients with lines. If you're interested in other curves and correlation and a lot of that stuff, take a stats class. They will beat it to death. For us, we're only going to deal with linear functions and linear regressions. Turns out that we can do regressions, and we will for other functions, but we won't talk about the statistical significance of correlation and what that means. So the symbol for the correlation coefficient has symbol lowercase r. And that comes from, in statistics, they don't call it the correlation coefficient. Well, they do, but the official name is the residual, and that has to do with some stuff from matrix arithmetic, which we'll see later. But it's really just a distance from something else that's being normalized. All right, so in this one, we would say that the slope of this line is negative, so our data is negatively correlated, and I would say yes, this is a good prospect for a linear model. Our data, while not perfect, does appear to be linear as we move from left to right. All right, we now take a look at our next graph, the one to the right, when I look at this data, does it appear to be linear? And I would say no, this is not linear. In fact, if I had to guess, what might be a good model for that set of data? Looks a little quadratic to me. It looks a lot like a parabola, right? So quadratic maybe. There's some other functions. It might be a sine curve or something else. And we'll talk more about other types of regressions, as I mentioned, later. So now we look at our next data sets. And if I were to look at this data set right here, does it appear to be modeled by a line? And I would say no. That data seems like it's all over the place, right? It's kind of spread out. It really jumps down in the middle. So it's definitely not linear. But once again, maybe, not a very good one, but parabola maybe? As I mentioned, it wouldn't be a very good one. It's a little off, but it could be some kind of parabolic curve maybe, or something else. And then lastly, when we look at our last picture over here, what do we think? It's not very good, but it's linear maybe. Not very good. So this is where the correlation coefficient is going to come in handy. So for this one, our data does appear to rise as we go from left to right, so we would have slope as positive. So that would tell us that our R value would have to be greater than 0. So besides telling us the slope of the trend line, R tells us something else. The correlation coefficient R is a measure of how well the approximating line fits the data. So the first thing we need to know, R is always in between -1 and 1. So it's normalized to have a value between -1 and 1. If the absolute value of R is greater than or equal to 0.7, the line is a good fit. If the absolute value of R is less than 0.7, the line is not a good fit. So what the correlation coefficient is really measuring is it's what's called the least squares distance from the line to every point. So if you imagine in this picture, if you were to calculate all of these distances, here, so D1, D2, D3, D4, D5, D6, D7, D8, D9, and then square them take the square root and then normalize them by a certain amount to get the ratio r, it tells you on average how far you are away from that line, which is what we're really going for. And then the goal of a linear regression is to minimize those distances. Because I drew this line, but if I drew a different line, I might be able to get a better approximation. Well, what if I had a line that looked like this? It's closer to some points and further away from others, but it has a different slope and a different y-intercept. It may be a better approximation than the other line. Our goal is, out of all possible lines that we can create, we want to find the one that minimizes the distance from all data points. So this can be done by hand, but we are not going to do it this way. We will do it using technology. We will do it on our TI graphing calculator. This can also be done in Excel worksheets and a whole bunch of other things. So linear regressions get used a lot when we need to do trend analysis. So speaking of trend analysis, there are two other things we need to talk about. So for example, if we have our data set that we're going to look at here, for example, number 2, let's go ahead and actually create a scatter plot for these. So the table below shows the net generation in millions and million kilowatt hours. Plot this data and determine if the data appear to be linearly related. So I'm going to cut the bottom off the graph. Let's try that again. So our grid, in this case, you'll notice, is not labeled. So the first thing we're going to need to do is analyze our data set and choose the appropriate labels. So it appears on our input axis, or row 1, that we have time, and on our output axis, it appears we have million kilowatt hours. So we have the year 2013, 2014, 2015, 2016, 2017, 2018, and 2019. So I'm going to start by labeling some of these on my graph. So we'll start with 13, 14, 15, 16, 17, 18, and 19. I actually wanted that one more back. There we go. So then if that's the case, this would be 12, 11, 20, and 21. So then on our vertical axis, it appears we start at 9,000 and we end at 72,000. And let's see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 ticks. So let's go ahead and start down here at 0. And we'll do 10,000, 20,000, 30,000, 40,000, 50,000, 60,000, 70,000, 80,000, 90,000, and 100,000. So let's go ahead and plot our data points. So in 2013, we're going to go up to 9,000-ish, here. 2014, we're going to go up to 17, so about here. In 2015, we're going to go to 24. We're about in the middle, almost 25. In 2016, we're going to go to 36. In 2017, we're going to go up to 53. In 2018, we're going to go up to 63. And in 2019, we're going to go up to 72. So when we look at that data, indeed it appears to be pretty linear, right? In fact, I could draw a line that looked something like this, right? And it looks like for the first few data points, it actually only goes through maybe 2 or 3 of them, but then I have 2 data points that are below and 2 data points that are above. So that's a pretty reasonable approximation. So I would say yes, the data is linear. So our data set that we were given starts in the year 2013 and ends in the year 2019. So on our graph, that would mean we have some data here and here. So this zone right here, between the extreme values on our data points, if we use this line to approximate, this is where we call it interpolation. So we are filling in, if we were to use that line to make an estimate of something where it's in between our data points, our data point max and our data point min, we call that interpolation. When we are on the outside of said data, so here our last data point was at 2019, this is when it's called extrapolation. And it would be the same thing over here. So what that's saying is when we are using a data set to come up with a model, if we use the line that we find to estimate a data value that's in between x min and x max, it's called interpolation. That is the best case scenario. When we move outside of our data set's range, we are doing what's called extrapolation. And extrapolation is a little more precarious. It is a very useful modeling strategy, but we have to be careful because we don't know really what's happening out there. So when you look at different statistical models, they will talk about extrapolation, which is something we do all the time, but we have to be careful on how we interpret that data, because interpolation is much more accurate than extrapolation, because we're basically trying to predict something that would happen in the future, and the trends might be changing. So, one last thing about this, looking at our blue line, would our correlation coefficient be positive, or would our correlation coefficient be negative? So our data is going to be positively correlated, so R is bigger than 0. And since our line looks pretty close to our data points, R is going to be close to 1. All right, so now we've been dancing around this idea. So let's go ahead and all grab our graphing device, because we are going to find a linear regression. So this is how we are going to do it on our graphing calculator. So this next sheet is just a walkthrough of the button pushes that you're going to need to do in order to get a linear regression. So let's all grab our graphing calculator and go through this together. So let's turn on our graphing calculator. So we want to find the line of best fit for this table of data, 0, 2, 2, 4, 8, 0, 3, 4, 5, and 7. So to get started, we're going to press our stats key, which is right in the middle of the calculator in technically the third row, but not including the function keys, the second row right here. We press stat. And then the first thing we're going to need to do is, we're already on it, we press stat and we choose edit. So we have our list menu here. So a couple of things, our X's are going to go in the L1 list and our Y's are going to go in the L2 list. So we'll see our headers up here, and some of you may already have some junk in your lists. So let's talk about list management for a moment. So say you already have some things in here and you want to clear that list. You can go through and delete them one by one, but that's a giant pain. If you just use your arrow key and you go up until you are in the header L1, you'll notice it says L1 equals down at the bottom, and then it has that list. Go ahead and press your clear key and then press enter. And it will delete every entry in that list. So be careful. Notice I said hit the clear key, because our calculator is really particular about this. So if I go up into my header, I might erroneously believe that I can just delete this. Seems reasonable. So I'm going to do that. I press my delete key, and similar to what happened before, it disappears. But what is different now than what was there before? What's the very first column's label now? L2. I actually removed the list. When we get to the later steps and we try to do our linear regression, this will cause problems. In the event that you ever accidentally delete a list, what you need to do is press your stats key and go down to choice number 5 where it says Setup Editor. And then press enter. So you select it once and then you have to press enter again and it just says done. You're like, okay, that's weird. Then I press stats and let's go back into edit and look who's back. Oh, L1 has come back, and the worst part is, did it actually even delete any of my data? No. So when we're deleting lists, we don't actually want to use the delete key. We go up into the header and we press clear. So that's one of the quirks on our calculator. Just be aware, because it will cause problems if you're deleting lists. All right, so now L1, we're going to put in our X's. So we go 0, 2, 2, 4, and 8. We use our right arrow, we go to L2, and in L2, we're going to put our Y's. So we go 0, 3, 4, 5, and 7. So we've now successfully entered our X's in L1 and our Y's in L2. These lists absolutely have to have the same length. So make sure that you've entered all of your data. So now that we're done putting this into our list, we are going to press our second key and Y equals. We are going to go down to choice number 5 and choose plots on. So you hit plots on, press enter one more time, and it says done. So now what we can do is if we press our graph key, we'll notice now that all of those points that we put in the list have been plotted on our graphing calculator. So we've just created a scatter plot of that data table. So we look at it and we're like, it's pretty linear looking. So we're going to say thumbs up. Yeah, this data is pretty linear. We've got a nice scatter plot. So now we move on to B, and it says use your graphing calculator to find the linear regression for the data set. So to do this, we are going to press stats, and then we use our right arrow. We're not going to edit this time, so we right arrow over to calculate. We are then going to scroll down to choice number 4 for a linear regression. We hit enter, and then our calculator is going to show this screen. We can either press enter or use our down arrow until we get down to store regression equation. Once we get down to store regression equation, we are going to press alpha and trace and store our equation as y1. We press enter again, and we should get something that looks like this. So we get y equals ax plus b, and it tells us what a and b are. When we do a linear regression, our calculator makes the slope a instead of m, but that's our linear regression in b. So some of you, on your calculator, it may show an r equals and an r squared equals on your calculator. If that's already showing up, take a nap. Everyone else, if your screen looks like this, we need to turn something else on. So if you look like this and you don't have your r and your r squared, I need you to go up here and press your mode button on your calculator. And then we are going to scroll down. If you have one of the black and white ones like my emulator, you have to scroll down to the next screen. On the color ones, they're all on the same thing. We're going to go down to the line that says stacked diagnostic. If the r and the r squared are not showing up, it is set to off. Use your right arrow, go over to on, and press enter. And that will turn your statistical diagnostics on. So after you've turned your stats diagnostics on, go second and quit to get back to your home screen. And since we've already put the linear regression in, we can just press second and enter to pull up what we did on the previous line. And when we do so, we now get the same 3 first lines, and we get our r squared and our r. So what does this tell us our correlation coefficient is? Well, we get 0.929. So according to our correlation coefficient, what we've done so far, it tells us that our data is a good fit. Because remember, anything above 0.7, we are going to call a good fit. And our scatter plot, let me grab that guy. So now when I press graph, since we stored our regression equation in our calculator, when I press graph now, not only does it show the scatter plot, it also graphs the line of best fit. So when I look at my data set, the line appears to be a reasonable approximation of that data set. So as we mentioned, we're going to say that the line is indeed a good fit because r is bigger than 0.7. So we have r is bigger than 0. So the data is positively correlated. .91 is bigger than 0.7, so it's a good fit. The line is a good fit. And what is the equation of our line? Well, if we round it to, let's do 2 decimal places, it says A is 0.79 and B is 1.26. So we have y is equal to 0.79x plus 1.26, approximately, right? We saved the exact value into our calculator, but that is approximately our linear regression. And as our correlation coefficient is 0.92, sorry, I wrote down 0.91, so I'm a crazy person, we would say that the line is a good fit. So now the last thing we were asked to do was use the linear regression from above to estimate the output when x equals 15. So if we are doing an estimation of x equals 15, are we doing extrapolation or are we doing interpolation? So what was our smallest x and what was our largest x? So between 0 and 8, for 0 less than or equal to x less than equal to 8, that's going to be interpolation. And for x less than 0 or x bigger than 8, we're going to have extrapolation. So in our case, if we are asked to do when x equals 15, that's going to put us here. So we're going to be extrapolating from this data the output when x is 15. So to do this on our calculator, since we saved our regression equation as y1, we just go to our home screen, we go alpha trace, choose y1, parenthesis, and 15. So it tells us that the corresponding approximation is this value. So we would estimate or extrapolate that the corresponding output when x is 15 would be 13.16. If we use this equation that we rounded, notice if we go 0.79 times 15 plus 1.26, we're going to get something close, but because we did all that rounding, we were accurate only to 1 decimal point. So we need to be very, very careful. When we're doing this type of computation, we don't want to round too early. If we do, we will introduce error and things will get marked incorrect. So just be careful not to round too soon. So in general, we want to use the unrounded values until the very end and then round to whatever we're supposed to. So if we're not storing our regression equation in our calculator and we're using some kind of rounded values like we did up here, I rounded to 2 decimal places. When I did so, it actually increased my error all the way to where my accuracy was only good to 1 decimal place, not 2. So we have to be a little bit careful. So one of the common problems that happens when people miss these problems is they do everything correct and then they just round too soon. So as a good rule of thumb, always just store your regression equation and don't round too soon. All right, so that's basically how we are going to find a linear regression on our calculator.